Hi, I'm Greg Lazenby, and my partner is Rebecca Hallsapple. The purpose of this project was to build and assess the usefulness of various time series models that will be used to predict flight hours. The number of hours flown or flight hours is an important factor for any commercial airline. Duty limits imposed by the FAA are based on flight hours, and aircraft maintenance intervals, in part, are based on flight hours as well. Our data set comes from the Bureau of Transportation Statistics underneath the DOT. We extracted flight hours along with other variables found in the carrier on-time performance data set. We aggregated the data daily and filtered to American Airlines flights originating out of DFW during calendar year 18 and 19. We began by checking for stationarity. The realization has pseudo-periodic behavior with peaks and troughs that fluctuate from week to week. We see consistent low points that are associated with Saturday, and as a former commercial pilot, I know that there are consistently fewer flights on this day, so we know the data violates one of the three rules of stationarity as it depends on time. In the realization, we see evidence of a possible yearly trend and increases at about mid-year along the summer months, along with some wandering behavior. The autocorrelation shows a spike at lag 7, and the spectral density provides evidence of period 7 with peak at 0.14. The spectral density also shows signs of frequencies at approximately 0.29 and 0.42. And these are likely seen in the autocorrelation, where we see smaller spikes at lag 3 and 4, which relate to the peaks that we saw in the realization at the first and later part of the week. We evaluate our models using average square error, or ASE, and run both a single ASE using 23 months of data in December 2019 as the test data, and a windowed approach where we train on 70 days and test on 31 days. We will populate a table similar to what's shown here and compare the performance of each model. Since we suspected weekly seasonality, we generated a pure 1 minus b to the 7th factor table and then overfit a factor table with p equals to 10. As shown here, the 1 minus b factor was the strongest. The second factor was relatively strong and a good match, but this factor was particularly far from the unit circle. The last one was a bit suspect as well. However, given the evidence, it made sense to model this weekly seasonal data model. We began by differencing the data to remove the suspected 1 minus b to the 7th, and the realization appears to have a constant mean. We have non-constant variance and strong evidence against white noise. After differencing, we have a strong lag at 1 and 7. The 1 may indicate the wandering that we suspected in the realization. IDing the model with AIC, we see the MA1 model scored the lowest, and we move forward with that model. We estimated the model parameters with maximum likelihood and show here a plot of the residuals. That lag 7 is still present with fairly significant lag, but otherwise the autocorrelation looks good. The realization still looks to have some structure to it and non-constant variance as well. The forecasts are shown here, and we see the last pattern repeated, but here the previous dip on Saturday that was significantly lower than the rest is carried forward, which makes our forecast have rather large error. The single run and windowed ASCs are shown here, and it should be noted that we also tried differencing the data as well with the first difference in combination with that 1 minus b to the 7th, but the results were kind of similar, and those lags in the autocorrelation, we just couldn't get them out of there. So even though the p equals to 7 was not suggested in AIC5, we believe there was some weekly seasonality and estimated the model with p equals to 7 and q equals to 1 using that 1 minus b to the 7th difference data from earlier. It's not shown here, but the realization still shows some structure in the residuals, very similar to the previous realization shown earlier, and again rejects the null of white noise using the Young box test. The autocorrelation of those residuals still show significant lag 7s. The forecast came out better by adding in that p equals to 7. We see the low points have less error than before, and both our single and windowed ASE improved. Since we saw evidence of the wandering in the realization, we decided to difference the data to remove the suspected 1 minus b. Both the AIC and BIC scored an ARMA 8-1 as the lowest. Model parameters again were estimated with maximum likelihood estimates, and again we're still not able to model out all the signal, but this time significant lags had been removed. The factor table here aligns much better with the frequencies we saw earlier in the Parzan window. The forecasts for this model are our best yet in terms of both the single and the windowed ASE. the forecast have pseudo-cyclic behavior following that weekly pattern and dampen as they get further into the future and tend toward the mean as that uncertainty grows. So next we tried a neural network approach and used day of the week as an indicator variable with differencing order of 7. We tried several different cross-validation runs to choose the optimal number of hidden knowns, but in the end, 5 nodes and 20 repetitions had the best results. We let the function optimize the lags, and the single run ASE here was very close to that of our very first model. But we felt we could improve and ran it under several scenarios. The best performance was gained by letting the function choose the regressor lag of 4, and it was the best single run ASE and one of the best windowed ASEs yet. So our final model was a simple linear regression model with categorical features. Since we saw that wandering behavior, we used the first inference data, but used a categorical day of the week indicator variable. The residuals are shown here and look similar to what we see previously, failing to model out all that signal, but we saw great performance when testing on just the December 2019 data, and it's pretty good for such a simple model. Here's a summary of the model performance. In terms of best, that really depends on the use case and the time frame that the model, but personally the ARIMA 811 was my favorite because it scored the best on the windowed ASE, which means it's likely to be a more robust model.